chaired the session when very active and very well-known people are speaking in this conference. So now we have B anomalies and EFT talk to be given by Professor GINO ISIDORI. He is at Physics Institute, University of Zurich, Switzerland. Professor ISIDORI obtained his PhD in physics from University of Rome, La Sapienza, and was postdoctoral fellows at SLAC and later at CERN before he moved to INFN laboratories in Frascati. He became the director, INFN research director in 2018. He, of course, had various visiting positions in between at Pisa, Munich, and at CERN. His research activities focus on the theory and phenomenology of fundamental interactions. He provided seminal contributions in the area of Higgs physics and flavor physics, both within and beyond the Standard Model. But his most influential results include the demonstration of the metastability of the Standard Model vacuum and the formulation of the hypothesis of minimal flavor violation. Since 2014, he is a professor at the University of Zurich, and his group is playing a leading role in the theoretical interpretation of the B physics anomalies, which have become very important and very exciting in recent years. So today we are going to hear more about it. So I request Professor ISIDORI to get started. Thank you for agreeing to give this talk.
John,
Bene, grazie. Ciao, John. Nice to see you. So it's a big pleasure to be here, even if remotely. And okay, let me start to share. And thanks for this very kind introduction. Yeah, there is always the problem of is it okay like this? Full screen?
It is not full screen as yet. You could.
I don't know.
Control F you could do, but it's okay maybe.
Let me try it again. So for me, this is a full screen. Oops. Do you see it now or?
We see it, but earlier it was better, no? What you did, but it's okay for me.
Yeah, now I cannot do it anymore as before. So.
Yeah, it's okay.
Okay, so if it is okay, let me go. Okay, so that I will discuss about these things about the flavor anomalies. I mean, really in the bigger context of flavor physics. So this is the plan of my talk. I will have some long introduction about flavor problems, and then I will go to these anomalies, which are really the recent hopes that there is something interesting going on in flavor and more generally in physics beyond the Standard Model. So as you know, I mean, we have the Standard Model is a beautiful theory that describes very well all what we observe, almost all what we observe in experiment, and is a very simple theory in a sense with a limited set of elementary constituents, quark, leptons, the gauge boson, and the Higgs. But of course, we think this theory is not the end of the story because it leaves unanswered some deep problems like the hierarchy problem, the flavor problem, particularly that the flavor problem is what I will concentrate most in this talk. So we think that is an effective theory. That is the limit in the range of energy and coupling that we're able to access of a deeper theory with more degrees of freedom. So what we used to call the Standard Model is just, if you want, the leading part of a series in an expansion of a bigger Hamiltonian, bigger Lagrangian that we have not yet fully understood what it is. So we think that there is out there a ultraviolet completion that I would call generically UV theory. And the low energy limit is the Standard Model. In particular, I'm concerned with the completion of the Standard Model where new degrees of freedom are heavy. Okay, so what we know after the first phase of the Large Hadron Collider is that the Higgs boson is there. This was found pretty soon. So the Standard Model spectrum is complete, and very important, there is a mass gap above this spectrum here. This is why we think there is something else, but we don't know exactly what it is because of this mass gap. So it's very difficult to try to reconstruct the UV theory given the mass gap, and that we don't have enough energy to directly see the degrees of freedom. So if you want just to starting slowly making an example, what we have identified are really the large scale structure of the theory. We want to understand if there is a deeper inner structure. And again, without breaking the pieces here, it's not easy to understand it. And we know that also from experience, because actually what we did before in the previous 30 to 40 years was reconstructing the standard model from its low energy limit, which is the Fermi theory and so on. So how can we do that to reconstruct the ultraviolet completion? Well, in absence of direct signal, the best things we can do is to try to understand if there are unnatural feature of the EFT that we still see at long distance that point to the fact that maybe we have not fully identified all the puzzles of our construction game. Okay, so if you see something that you cannot reconstruct with the piece you have, it means that even if it is macroscopic, it signals that there is something microscopic that you have to identify. And flavor physics, I will try to convince you, really plays a very, very important role in this game. And we'll explain it now, and we'll play it even more in the next 10, 15 years before the possible new high energy collider. So let's look closer to this flavor problem. Why anti-flavor is interesting is maybe it's telling us something. It's a very old problem. It's with us since a long time. I think the first probably who posed the problem in modern language was Isidori, who, when the muon was discovered, so it's the first copy of one of the other existing particle with the same properties and different masses, said, but who ordered the muon? Okay, and now we can say the same thing, who ordered the other families. So we can formulate this in a technical term, this flavor problem, looking deeply to the standard model effective field theory, in which you already heard this morning about the SMEFT. So we have, the SMEFT is constituted of the gauge sector, the Higgs sector, which are the classical standard model part plus the tower of higher dimension operator. So the gauge sector is really describe the long range forces of the standard model particles. So their nature and how they interact with these long range mediators. The Higgs boson is there to describe the masses, and these are the operator of dimension up to 4 that we can build with this ingredient. And then there is a tower of extra term that is the remnant of the heavy dynamics at low energies. So if we don't have enough energy to excite any degrees of freedom, we can describe their effect as a series of local contact interaction, which will be more and more suppressed by this scale lambda that parameterize the scale of new physics. And technically, these are the operator dimension more than 4. Now, if we stick here to the gauge sector, so this part that describes, if you want, the long-range structure of the theory, this is highly symmetric. The structure is fully dictated by the number of light fields and their charges under the long-range interaction. And looking at this charge, we observe a large degeneracy. Actually, first of all, the gauge coupling, everything is very natural, all order 1 parameter. And then we have these flavor degeneracy. So we have one families of up, down, electron, neutrinos of different field with different charges under the electroweak group. But then this is replicated 3 times. So if I move here, this table, left or right. So if I move from one generator to the other, nothing changed from the point of view of, yes?
Yeah, Professor, the slides are not changing.
Do you see something changing? It's only changing here. Okay, it's a small change. Can you see it now, moving it? But we're just illustrating that if I move here, there is a white thing that moves. So to which slide are you? Is there?
We are still on the
slide 2.
Slide 2.
Slide number 2.
Oh, sorry, that's terrible. You should have told me before. Shall I do it? Maybe
and now it is okay.
Maybe I should do it. Okay, so let me.
And just 1 second. So maybe besides this customize, there is 2 arrows. If you click on that, maybe it becomes full screen.
I think trying to make it full screen was the problem. Now, can you see it now moving it?
Yeah, it's moving.
So maybe it's better I don't do the full screen. It's better I leave it like this.
Okay.
How big is what you see? Maybe you just see the things around.
This is fine. I mean, we can see clearly.
I'm very sorry because I think everything was based on the maybe so I restart briefing ourselves from here. So I want to say, okay, we have the standard model and the UV completion, and we have this mass gap. Okay, and that is my illustration about the long range and small pieces. And Okay, and this is what I say, that we really want to look at the unnatural feature of the EFT. And finally, here I was starting to with flavor. And okay, here we are. Do you see this MEF Lagrangian in the upper part?
Yes.
Yes, yes.
Yes.
Okay, sorry again. I mean, so okay, here really starts the technical part. So here I have to slow. So what I'm saying, we have the gauge sector, these long range forces, the Higgs sector to describe particle masses, and the higher dimensional degrees of freedom that describe the heavy dynamics. Okay, so here in the gauge sector, we have this flavor degeneracy. So we're saying if you look at the charges here of the first family, now if you look at the second family, third family, the charges are unchanged. Okay, which this means that there is a big flavor symmetry, which actually technically is U3 to the 5th symmetry. Now this symmetry in the standard model, it's broken by the Higgs sector. Okay, so we introduce the Higgs sector to describe particle masses. And as you know, these in the fermion sector, in particular, the interaction that plays the role is the Yukawa coupling. So the interaction with two fermions and the Higgs. And then when the Higgs get a wave, describe particle masses. So when the Higgs acquire a wave, these we can distinguish these different fermions because of their different coupling to the Higgs. And we observe different masses, not different charges. And the Yukawa couplings are very peculiar because they are very hierarchical, corresponding to this very hierarchical spectrum with the up quark, and the first family very light, then the second family is a bit heavier, and third family even heavier. And so actually this is reflected, but these Yukawa coupling are 3 by 3 matrices in flavor space. So we have a big entries, which is the top Yukawa coupling, and then smaller entries when we go to the light families. This is what is sometimes called the standard model flavor problem, because this structure is very peculiar. So we span 5 orders of magnitude from the electron Yukawa coupling and the top quark Yukawa coupling. And there is no clear explanation for this. And if you try to throw random numbers, I mean, you get a very bad fit. I mean, it's very unlikely to reproduce what we see. So this means that this is not random. There is some explanation behind it. So the flavor sector of the standard model is described by these two factors. We have a large flavor symmetry in the gauge interaction, 3 identical replica of the same fermion family, and the specific peculiar breaking by the Yukawa sector. So the Yukawa interaction, first of all, break the symmetry only along certain direction, because it can couple left and right field, it cannot couple left or right. And also the Yukawa coupling are hierarchical. So putting these two facts together give rise to a series of exact and approximate accidental symmetries. I put here a question mark. We don't know if they are accidental or they're fundamental. I think they are accidental. Okay. What do you mean by let me just give you some example about these symmetries. So for instance, individual lepton flavor is an exact symmetry simply because we cannot, I mean, just having only one Yukawa interaction in the lepton sector, we cannot write something that differentiated automatically. We conserve lepton flavor. This is an exact symmetry simply because we cannot break it. We cannot write an operator that violates lepton number, individual lepton number at the level of dimension 4 and be consistent with the gauge symmetry. There are other symmetries which are approximate. There are many more. For instance, isospin. So isospin, that is the symmetry between up and down quarks, is there simply because their mass are very small. So we can neglect them in first approximation and say that they are equal to 0. This gives rise to isospin symmetry. So you see, it's really a peculiar structure which emerge, which maybe doesn't have really a deep explanation. It's just because we can break the symmetry only with a certain series of coupling. So more generally, these accidental symmetries is a very important concept in the effective theory. So are symmetries which are not fundamental properties of the theory, but they emerge accidentally at low energies or large distance because we don't have enough variable to describe the violation of the symmetry. It's a bit like the multiple expansion. When you do the multiple expansion in electromagnetism, first you see the charge, then, and the charge is very symmetric thing. Then to want to describe the inner degrees of freedom, you need the higher multiple. So it means in our language, it means you have to go to higher dimensional operators. So if there is some new dynamics that So if this is not a fundamental symmetry, you expect that at some level this symmetry is violated in the theory. Therefore, these new dynamics should induce a violation of the symmetry, which will manifest via the higher dimension operator. Cannot manifest here because simply cannot describe it. So if the symmetry is accidental, we expect it to be violated by the higher dimension operator. So searching for this effect, which are very tiny but clearly visible experimentally, we can probe high energy physics even if we don't really go to high energy. And yeah, there are very well-known examples from the past of that. I mean, just to make an example, just to probably the most famous one, in the old days when there was only the theory of strong and electromagnetic interaction. So we were not speaking about the Higgs, but we were describing particle masses with explicit mass term because these were compatible with QCD and QED. Then there is an accidental symmetry, which is flavor, but this accidental symmetry is violated by the Fermi interaction. Indeed, you see the interaction first. Interaction has been identified first in the charged current because of the U to D transition, which is a violation of the accidental flavor symmetry of electromagnetism and strong interaction. So even if the interaction was much weaker, you could see it because it was violating the symmetry. And you immediately have an indication of a new scale, which is, in that case, was the Fermi scale. Okay. And I'm stressing all this because actually this violation of lepton flavor universality that now seems to emerge from data are exactly of this type. Okay, and that is where we will go now in a minute. On the other hand, in principle, there are many violations of a symmetry that we can expect to see, and we don't see them. Okay, so for instance, a typical example is if we look at process like meson anti-meson mixing. If here there is a higher dimension operator that does not respect the flavor symmetry that we have here, this could give a big destabilization to meson anti-meson mixing. Amplitude, we measure them, we don't see that, and we express what we don't see as bounds on the scale that suppress this operator, assuming a coupling of order 1. So beside the B anomalies, we don't see any other deviation. And you see actually here the bound put on the scale of the higher dimension operator, assuming a coupling 1, which is a strong assumption. You see one can reach even bound up to 10 to the 5 TeV. And this is the other problem of flavor, which seems to indicate that maybe, okay, if really there is no symmetry at all, maybe new physics is at very heavy scale. Is this the case? Well, here again, we have to be careful and looking into this concept of accidental symmetry. Because if there are accidental symmetries, we can separate scale in the effective theory. So a typical example is neutrino masses. As you know, we can describe neutrino masses in the SMEFT, putting a higher dimension operator, dimension 5, which is this operator here, which violate an exact symmetry here, which is lepton number. Now, neutrino masses are very small, below 0.1 electron volt. So we can attribute the smallness of this operator to the heaviness of the scale where lepton number is violated. So this scale can be very, very heavy, like 10 to the 10 TeV. But this doesn't prevent to have lower scale where lepton number is conserved. So you see, we have a separation of scale. And so it's consistent to assume even the operator of higher dimension, like dimension 6, appearing at a lower scale, provided you don't violate lepton number. So it could be that, for instance, the heavy scale associated to Kekebar mixing, it's heavy, but nothing prevent to have a lower scale of new physics and maybe even violate flavor, but do not contribute to Kekebar mixing. So if one can make construction of this type, separating the scale. So this separation, which I think everybody accepted for the exact symmetry, but can hold to a certain degree also for the approximate symmetries. So summarizing all this discussion is general discussion about flavor. So in the anomaly EFT, we have this large degeneracy, large accidental flavor symmetry coming from the gauge sector. We have a peculiar breaking from the Yukawa coupling, and then we have a series of stringent bounds on the higher dimensional operator. So the big question that we want to address is, are really all these symmetries here accidental, or some of them are more fundamental? At which scale are they broken? In particular, can we make sense of the tight bounds on new physics from flavor violating process and still hope to see some signal somewhere? And in this case, where? And I think this concept of accidental symmetry and scale separation you will see play a very important role. And what I argue is that recent data really seems to go in a precise direction, which is consistent and could really be consistent with the explanation of the hierarchies that we see, and also with the existence of new physics not far from the electron scale. Okay, so this is what I want to say about the as introductions, and now go more into the topic of these anomalies. Do you still see the slides? You're sleeping. Okay. Can you follow?
Yes, we do.
Okay, yeah. Give me feedback if I go too slow. I mean, you can interrupt anytime. Okay, feel free. Okay, now
it's fine with us.
Yes. Feel free to interrupt anytime. Whenever. Now I'm changing a bit, so I go really to the topic of the anomalies. So since 2013, results in electronic decay started to exhibit some tension with the anomaly prediction connected to a possible violation of electron flavor universality. So we seem to observe a different behavior of beside kinematical effect of different lepton species. And we see this in B2S LL transition. So we see a difference between mu and electron in this case, and also in B2 sharp lepton neutrinos, where we see a difference between tau versus the light leptons. So first of all, what is lepton flavor universality? Well, lepton flavor universality is one of these accidental approximate symmetries of the standard model Lagrangian. So is a symmetry that we have in the limit where we neglect the lepton-Yukawa coupling. So if I switch to 0 the lepton-Yukawa coupling, I have a symmetry. All the leptons appear as identical particles from the point of view of the gauge interaction. Now, this universality is badly broken in the Yukawa sector because the Yukawa couplings are very different. 10 to minus 6 for the electron, 10 to minus 4 for the mu, and 10 to minus 2 for the tau. However, they are all very small. So you can neglect them in first approximation when you compute a decay rate, except for pure kinematical effect. So it's a good approximation usually to neglect this Yukawa coupling except for determined particle masses. And in that limit, we get what we call lepton flavor universality. But you see, it's clearly an approximate, not in fundamental. I mean, in the only interaction that can differentiate the leptons are very different. But the strength of this interaction is very small, maybe accidentally. So maybe in other sectors of the theory, we can have a stronger distinction with a higher strength, okay, of interaction. So let's look at the as a glimpse to the data. So let's start with B2SLL. So here there is really a high significance, and several observables pointed to the same coherent picture. The first cleanest observable are this ratio. I mean, a ratio of a hadron with a big quark decaying to a hadron with an S quark and two muons normalized to the same transition, exactly the same transition, but 2 electrons. So these are the standard prediction, which is basically 1, because you can neglect kinematical effect. In this case, it's slightly less than 1. And these were the experimental result till 2 years ago. Now, new result came out. This one has become more precise. These other things are new, and you see that they're all below the standard model prediction. Really, they form a nice coherent pattern when you average them. And the significance start to be high because, okay, 1 is 3 sigma, but there are a lot of others which add significance to the anomaly. And these are all different observable if you want. Then there is another observable which is completely different, which is the branch ratio of BS mu. In this case, actually, it's even a different experiment because this is the result averaging ATLAS, CMS, and LSEB. And here we can directly compare with the standard model prediction, and you see that there is a deficit, exactly like here, there is a deficit. And this is only 2 sigma, but it's very consistent with these others, as you will see. And finally, there are these other anomalies, which are in the angular distribution or in the branch ratio, where again, we see a suppression of the muons, while in this case, it looks like an enhancement, but this is an interference effect. So again, it's a negative amplitude for the muons. All of this is nicely coherently described by a same local BS mu interaction. Of course, we will discuss here, the theory error is bigger, but even if we just stick to this, the significance is high. So how we describe this data? Well, to describe BS LL decays, we have to build a even a lower energy effective Hamiltonian, integrating out the W, the Z, and so on. You have to evolve down to the B scale, and then we have to evaluate the hadronic matrix element. This is the typical, the generic structure of this four-Fermion Hamiltonian, which contains operator like this O10, B2S, and leptons in the axial current, or B2S LL with the axial in the vector current. This is O9. Then you have to evaluate the matrix element. This is the easy part. The difficult part is that you also have operator like B2S charm. Okay, this part is more complicated to evaluate. You see, it's hit the possible non-perturbative effect. So this is difficult and can mimic the same effect of this operator 9. Okay, so they mimic a point-like interaction. However, this long distance effect cannot induce a violation of universality, because here the photon attached universally to electron muon. So this is why these LFU ratios are clean, and also cannot induce a correction to the axial current, because again here there is a photon. So this is also why BSB mu is clean. Okay, that is the distinction between clean and more complicated observable. And if we just look at the clean observable only and try to fit them, so we fit the coefficient of this C9 and C10. In this case, we really fit the difference between electron muons. We see a very nice consistency of these ratios and BSB mu. And there is a very high significance. It's 5 sigma. Okay, now putting all the data, all the recent data, 5 sigma, if you assume that new physics is left-handed. Okay. If you make more hypotheses, the significance goes a little bit down, but still it's a high significance. So comparing 1-to-1 standard model versus this hypothesis is 5 sigma. Now, here, if I put also the other observable, those more affected by long distance, I need more parameter to describe well the data. So not only a left-handed correction, which is this delta C9 equal multiple, I also need a universal correction. So a same correction for electron muons. But once I switch on this effect, the two data are perfectly consistent and very far from the standard model. Actually, this here, the significance is much higher than 5 sigma. Then if I really want to play devil advocate and I look at all possible new physics hypotheses of short distance origin, the significance, then there is a kind of look elsewhere effect, and the significance goes down to 4.3 sigma, but is a super extremely conservative estimate. Okay, I think the significance is higher than that, because I believe that here, okay, here not looking at all at the other observable is too conservative. We're also looking at completely extreme new physics hypothesis is not very motivated. So I think the significance is between 4 and 5 sigma, but it's very high. Then there is the other class of anomalies here with the more brief, which are B2 charm, the charged current anomalies, where we see this ratio R, which is the ratio between taus and lepton modes. And also here you see these are the experimental results. They average well, they're well consistent with a good probability. And the standard model is down here. There is a 3 sigma tension here. Here the progress is much lower. So most of these results are a bit old. I hope there will be new coming soon. And also in this case, we are consistent with the left-handed amplitude, because you see if the amplitude is left-handed, you just expect to live in this band here. And so data are perfectly there. And the effect is much bigger compared to the previous one in absolute term, because here we are competing with the standard model at 3 level. Okay, so these are the data. Now, having briefly listed the data, let's first now look at the consideration of what could be behind these anomalies. Okay, so anomalies are seen only in semi-leptonic operators, quark lepton operators, and we definitely need left-handed operators. Maybe there is something else, but we cannot do without the left-handed ones. So let's start with these minimal things. Just put left-handed new physics operator connecting quark lepton, something of this type. We see something big in absolute term in the B2 charm tau decays. We see something smaller in B2S muon. You see here, I put second generation for the muons, while tau and new tau is third generation. So clearly this operator has more third generation field, only the charm is second generation, while in this case, there are several second generation field and the effect is smaller. So this fits very well, at least qualitatively, with the idea that there is something large for third generation. So new physics really is big for the third generation, and then becomes smaller and smaller when we go to the lighter generation. And this is a very nice link to what we see in the Yukawa couple. This is why I'm interested in by this effect, because it seems to go in the direction of connecting to the origin of the Yukawa hierarchies. So let's try to quantify better what we observe in terms of effective operator. So all the data are described by operator of this type. Okay, stable electronic left-handed operators. You see quark, lepton, lepton, quark. I call this operator ij alpha beta, where ij and alpha beta refer to the flavor. So the most significant effect is this B2S mu operator, which I call 2,3, because referring to the third and second generation of down type quarks, and mu, which describe this left-handed violation C9 equal minus C10 for muons. The strength of the interaction is very small, 10 to minus 5, the Fermi scale, 10 to minus 4, 10 to minus 5, the Fermi scale. So it's a kind of new super weak interaction that in this band here is this band here. Now, if we look at the other observable in B2SLL, okay, for which the significance is lower, but still there is some significance of deviation, then we need to describe this universal correction. This we can describe it again by this operator here, but switching on the taus and then closing the tau loops to leptons, as was pointed out by these authors, we can generate a universal correction. So in this case will be the same correction for electron muons, and it will be this is a much more suppressed contribution. So we need a much bigger contribution for the initial contribution with taus, which fits with this idea of a flavor structure. So indeed, you see here, this coupling LL23 is in units of 10 to the minus 5, because it's here it's 10 to the minus 3, and then there is another 10 to the minus 2 from the scale, and while this operator is much bigger. Of course, this is a possible interpretation. Maybe I can put by hand this universal contribution, not doing it via tau. But why I like this is that this operator was pointed out before it was observed from the charged current anomalies, because actually this operator now, if we take the SU2 partner, it describes B2 charm tau neutrino. So the size and the need of this operator was predicted from charged current before this effect was observed. So it's very nice that it's there. So now let's look at the charged current. So in the charged current, again, we describe everything with the same operator. Now, however, since we use as a reference basis the down quark, we have to do a CKM rotation. So for instance, if we want to describe something in B2 charm tau, we can have a 3,3, which means BB, and then pay VCB, or a 2,3, which means BS, and then pay VCS. So it will be a combination of these two, normalized to the standard model, which is VCB. And then therefore you have a band here in this plane, and you cannot go too far here, because otherwise you hit bounds from high PT observable with the 3,3, which is the biggest contribution here, because it's the one appearing with the smallest coefficient. So here you see the bit to C tau identify a band in this plane 2,3,3,3. Then I can use the information I had from neutral currents and I put everything together, and there is a nice overlap of the two, which are really very different effects. So this is really remarkable. So the information here from the universal shift in the SLL fit very well with the preferred region of B2 charm tau. Okay, errors are still very big, but this could be order of magnitude different. On the other hand, they fit. And so we start to see this pattern with something big for third generation, smaller when you put 1 second generation, and even smaller when we put 2 second generation leptons. So the idea here is that everything originates from so we see clearly this effect in B2S mu, okay, with a high significance, 5 sigma. And the idea that here there is a small coefficient because of several second generation field, but the original interaction is a much stronger interaction involving only third generation, which is BB tau tau. And this interaction with the CKM rotation contribute to RD, to the charged current anomaly. So we have this natural connection. And of course, there should be other intermediate step, because we can have not only B2S. So if here I remove 1 mu with 1 tau, I have B2S tau mu. Then if I remove another mu on 2 with the tau, I have B2S tau tau, and finally BB tau tau. So you see, you expect all this pattern. And interesting, and each time you go from here to here, you put a 10 to minus 1, because you put more and more second generation field. And so you predict a lot of effect. I mean, so you predict this universal correction, which indeed it's there. And then the combination of the two describe now really well the B2 data. So there is a nice consistency. Only one of the things is really clear, which is B2SLL, but the other, the less clear anomalies fit into this game. Of course, there are things that we have not seen yet, like B2S tau mu, but it's consistent that we have not seen it. And also PP2 tau tau, we'll discuss more in detail. You should see it relatively soon. And here, hopefully, you have something big associated to a scale which is not too heavy, like 1, 2 TeV, which maybe can stabilize the Higgs sector, which is still a bit of a hope, but it's possible. So summarizing what still at the level of EFT, what we have seen is that we have this nice pattern of same electronic operators. We also have to say what we have not seen. We have not seen seems to call for an additional suppression. So if I do the same scaling for a 4-quark operator, I'm completely killed by delta F equal 2, so K bar mixing, B bar mixing. Similarly, if I do the same scaling for a pure leptonic operator, I'm killed by tau 2 mu, leptonic. And even here, this specific combination, this is the good one. If I change here the sign, so if I don't do this specific contraction, I am in trouble with B2S nu. So I really need this as a starting point, which call for a leptoquark, because you see it's really a leptoquark current. It's not a QQLL. S3 level, the idea is that they have a leptoquark mediator generating this at 3 level, and then of course all the other are generated only beyond 3 level. And if we stick to the EFT, we can see more or less the size we can expect, because of course we can take this operator, when we close the loop, for instance, we can do this best mixing at the 1 loop level, or we can do tau leptonic at the 1 loop level. Here, of course, there is some dependence on the cutoff of the theory, because we are still at the level of EFT, but this is the region that you cut. So you see, you start to cut a significant fraction of parameter region, but there is a part of the region which is consistent with present data. And these are just qualitative indication. If I put here a cutoff at 1 TeV, so you can play with this a little bit, which is telling you that, okay, the system is constrained and certainly not ruled out. Okay, it's the maximum I can say, still sticking at EFT level. So let's now start to go to models, model building consideration. So to move forward and discuss models, we really have to address two things. I mean, the origin of this flavor structure and the mediator. And I already give you a hint of both. I mean, something connected to the Yukawa and something connected to leptoquark. So concerning the flavor structure, this idea, it's opposite to the old idea of minimal flavor violation. The old idea of minimal violation was to have only one big gap without flavor up to some very heavy scale. So the idea was to have, okay, the SMEF, some new physics at the TeV scale stabilizing the Higgs sector, and then flavor blind up to, let's say, Planck or unification scale. So that is what, for instance, you were doing in the MSSM. No? The idea was to concentrate on the Higgs and postpone the flavor problem. So to basically assume that we have these 3 generations as identical up to very heavy scale. Now, what this data is telling us is something that seems different. That is, we really have to use this opportunity how to have scale separation in the EFT, which are given by the approximate symmetries. So the idea is that we have some new physics close by, which however involve only the 3rd generation. And then we have at higher scale something that involves the 2nd generation, and further higher scale something that involves the 1st generation. This structure is consistent, is stable, because the Higgs interact very little with the 1st generation. I actually even explain why the Yukawa coupling of the first 2 families are small. So the same Yukawa, the same dynamics here generate the flavor hierarchies. Okay. So the Yukawa coupling of the light families are small because they interact with new physics that generate the Yukawa coupling at higher scale. So we really have to abandon this concept of identical copies. Really, there is a structural difference already at the TeV scale between the different generations. And so what we, of course, this is something that was discussed by several authors even before the anomaly were being described, and it fit very well with what we see here. And what we are starting to observe is just this first step here. Okay, now if I enlarge it, we have the first step between the electroweak scale and the first hint of new, and the hint of new physics that interact essentially only with the 3rd generation. the first two generation can be considered as massless, and there is only a small mixing, which is the same mixing that controls the structure of the equal coupling. So this is something again that was proposed before the anomaly were observed, this U2 symmetry, separating the first two families with respect to the third one, and is justified by the structure that we observe in the equal coupling, where we have in the limit of unbroken symmetry, only the third generation can have a non-vanishing equal coupling. So the idea is that this not only works for the equal coupling, but also for these new dynamics. Concerning the dynamics, if we ask which mediator describe well this data, and I already told you lepton quark are favored because they describe at the 3-level affecting semi-electronic operator and not at the 3-level for quark or for lepton operators. This is different, for instance, from a Z prime, which on the other hand contributed to 3-level to be submass mixing. So that's why lepton quark seems to be clearly favored in this picture. There's been a renaissance of lepton quark model. A lot of model discussed in the literature for these anomalies. I will not enter in all the possibilities. I will consider it only on one class, which I find particularly interesting, especially if we want to describe both set of anomalies. And this class is this type of U1, so-called vector lepton quark mediator, which you see the U1 is a vector field, which colored as a bottom quark and with no SU2 quantum numbers, which really transform a B into a mu1 or a charm into a neutrino. But for instance, cannot transform a B into a neutrino. So for instance, you see at 3-level do not contribute to BS, neutrino to neutrino. And really contribute on the other hand to the two anomalies we see perfectly at 3-level. And besides that, besides being perfect to fit both anomalies, it's the only one that does it as a single mediator. It also fits in a nice gauge group, which is the Patti-Salam gauge group, which will come back now in a minute. So indeed, already in 2015, we discussed with Barbieri and a few collaborators that the best possibility is this U1 field with the U2 flavor structure to describe its coupling. So now if I take this with more and try to do a fit with the most updated data, so I just, for the moment, just take the U1, okay? I don't discuss where this U1 can come from, but I just want to see if this is consistent with data. So we describe the coupling of this U1 with the left-handed. Now we put also right-handed quarks because in principle, right-handed fermions can be there. We assume a hierarchical structure for the coupling motivated by the Yukawa couplings. And then we discuss all the effects generated by this operator at 3-level plus dressing with standard model field, so including also infrared dominated loops like contribution to electroweak precision observable and so on. And what we get is a perfect description of all the available low energy data. So now this is an exercise that we did to fit all the available low energy data and the electroweak precision observable. You see this is a standard model point, while here you see these are the anomalous data, delta RK, delta RD star. These are the experimental result, and this is the fit that you get, which is perfectly described data, and the standard model is very far. You can describe well data with or without a red-handed current. So for the moment, we cannot distinguish the two cases. What is particularly important is that then you predict something in high PT. This is a prediction, okay? Now we have fixed all the coupling from low energy, and you predict what you should see, for instance, in this proton-proton to tau-tau via diagram of this type. So you have a B to tau T-channel scattering of the lepton quark or a pair production. The pair production cut a little bit of parameter space. Here we plot the favorite region is this one, yellow. The favorite region from the anomalies. You see that only a small fraction is cut out by the direct production. A fraction is cut out here more significantly from the T-channel exchange, and you see where we could reach with 3 inverse autobahn at the end of the high luminity. So this part will be all explored in the future. So it's very interesting. Actually, with right-handed current, there is a more fraction which is ruled out, but still a large fraction, the the best fit is not yet touched. And of course, you predict a lot of other things also in other rare modes, like tau to mu 5. So you expect a violation of lepton flavor in tau decays or in B decays. You expect a big enhancement of decay into 2 taus. All this is consistent with present data. Some of them start to be touched by present experimental searches, but I think the leading effects are still to be explored. So it's a very interesting prediction. Okay, in the last 10 minutes, let me go to speculation on the really deeper UV completion of all this, because I just put a mediator, okay, but this is a vector field, so it needs a UV completion, a massive vector field. So the idea here is go back to the Patti-Salam hypothesis proposed in the 70s to unify quark and leptons, because in this model, it was predicted to have a leptoquark exactly with this gauge quantum number. So the idea of Patti-Salam was to have SU4 as a group unifying color and lepton number. So fermions are organized in multiplet, 4-plet, where lepton number can be seen as the 4th color of SU4. So at this SU4 is decomposed into color, B minus L, and exactly the leptoquark we seem to observe in the anomalies, nothing else. So it's really fantastic. However, the original idea of Patti-Salam doesn't work because here there is no flavor. So actually this leptoquark will be universal. So would couple also to the light generation with the same strength. So for instance, you are completely killed by K-long to mu E, right? Because here we have S mu dE. If I put the same strength that I have in the V anomalies, I'm killed. I have to put here a much heavier scale. Well, the scale I need for the anomalies is 2, 3 TeV, 5 at most. So this doesn't work. So we can, if we want, circumvent this problem, adding more fermions or scalars. But there is another way which I like more, which is really to modify, on the other hand, to modify a bit the gauge structure and attack this problem really at the gauge, at the level of the gauge interaction. Take advantage of this fact, and the gauge interaction do not need to be flavor universal. So the idea is that instead of having SU4, we go to SU4 times SU3, where color now is not anymore a subgroup of SU4, but it's a subgroup of SU4 times SU3. So color, the true color we see at low energies, QCD, is a diagonal subgroup of a SU4 times SU3 groups, which are flavor dependent. That is, this one is felt by the third generation, and this one is felt by the first 2 generations. So it's very similar in a sense, if you think to what we have in electromagnetism. Electromagnetism is a separation of the symmetry in helicity space. So we have SU2 left and SU2 right, and then of course there is a diagonal subgroup, which is electromagnetism. We don't see any difference between the electron right and the electron left from the point of view QED. Like here, we don't see any difference between first and second and third generation from the point of view of QCD by construction. On the other hand, we see it when we go to the broken generators. Like here, we see it when we go to the W and the Z. There we see a difference in helicities. Okay, so the idea is that this happens at the electroweak scale. This breaking of in terms of helicity space, while this one happens at some few TeV, where we really differentiate between the third generation and the light generation. So this construction is very nice, and actually, starting from this basic idea that was being discussed by various authors already 3 years ago, there are a lot of other hypotheses which are kind of generalizations. So for instance, we can go to what we proposed some time ago, that was Patti-Salam cube, really 3 copies of Patti-Salam at different energy scale, or we can go to models with the strong dynamics, where these things like the model proposed by Barbieri, this come, and this SU4 is just a global symmetry, but this is more or less a generalization of these initial splitting. One class of model I'm particularly interested about, on which we are still working, is the idea that maybe all this is just an effect of a higher dimensional construction, where we have a kind of Patti-Salam symmetry in the bulk, and these different scales are different branes in the 5th dimension. So we have the third family localized more on the UV, And we break here the electroweak symmetry. So you see here the profile of the Higgs, which is of this type, while the profile of the breaking of the Patis-Salam, which is of this other type. So the first family, which is the more UV localized field, or if you want the field associated to the higher scale. At the higher scale, Patis-Salam is very badly broken, so you don't see the lepton quark. On the other hand, here, the electroweak symmetry is largely broken, so you have a big Yukawa coupling. But okay, this is just a possibilities among the many others. Now going back to phenomenology. So if what really matters is to have these at TV scale to have this gauge symmetry SU4 times SU3 times electroweak broken down to standard model. So you have not only the lepton quark, but now you have more generator here. So you have in addition a Z prime, but especially also a coloron. So a colored a heavy vector coupled mainly to third generation. This structure is apparently complicated. Of course, we have a lot of ingredients, but a lot of things are fixed by what we see at Length, so by the Yukawa coupling, by the anomaly. So at the end, there are not many free parameters. It's a highly constrained, renormalizable theory that describes very well all the data, including the anomalies. In this case, you can really compute precisely delta F equal to process, being mixing, and you are consistent with this. With data, similarly, you predict the effect on the high PT, which are borderline to what we don't see, and it's an interesting thing. One of the extra prediction of this UV completion is that not only you expect the lepton quark, as I said, you also expect this colored field, coloron, heavy color octet, coupled mainly to third generation. So you expect to see something, for instance, in PP2 top due to the exchange of this coloron. And these are the present exclusion bound, which indeed still are in the, for instance, if you live here with a large width that you expect in this model and the mass around 3 to 4 TeV, you are consistent, but you see this has to be a very important constant on the parameter space of the model. So to conclude, I hope I give you, convince you that flavor is an essential ingredient to understand the structure of the SMEF. And this statement is there, was there even before the anomalies, okay? And it's just that because of the Yukawa coupling, which are really peculiar, I mean. And of course, the anomaly reinforced a lot of this statement. The statistical significance of the anomalies is growing. In the B2S LL system, really, the coherence of the different results is striking, and the possibility that this is just a pure statistical fluctuation is marginal. If combined, so in the case of the charge current significance is lower, but then, I mean, once we have one significant, one anomaly, I think also I try to illustrate the nice consistency of the two things, so it's nice to put them together. So if we combine them, the two anomalies point to some non-trivial, seems to point to some non-trivial flavor dynamics around the TV scale, involving mainly the third generation. So, and really possibly connected to this origin of flavor, with this underlying idea of a multi-scale structure, which I think is very interesting. So there is no contradiction with all the other data that we have seen so far, both at low and high energies, but new non-standard effects should emerge soon, as I try to show you, in both this area. So I think it's a very interesting field with a lot of opportunities for the future, and both from the theoretical point of view and from the experimental point of view. Okay, thank you. And sorry again for the initial part where there was this problem with the slides.
Thank you very much. Questions, please. Anybody wants to ask any question?
So I have a question.
Yes.
So if I just want to combine G minus to mu with this B anomalies, then this vector, what is the status of vector like lepton quark?
That's a good question. I hope I have yes, some slides. Yes. So what about G minus 2? Because many people always ask me about this question. I would say it's not obvious how to reconcile the G minus 2 anomalies with both flavor anomalies. And more generally, I think it's difficult to reconcile G minus 2 with models with the natural structure connected to the Yukawa coupling. This is why I find it puzzling, because there are still, first of all, there are many unknowns on G minus 2. G minus 2 certainly cannot be a 3-level effect, okay? Any model has to be a generated one loop. It's a big thing. if we take it literally, for sigma, it's a bit more controversial because of this lattice result, but okay, let's take it to which scale it points. Okay, we don't know because it can be very heavy if you remove the elicited suppression, or can be much lighter if you take the elicited suppression as in the standard model. The main difficulty of G-2 and flavor is the strong flavor alignment that you need to avoid bound from E to a gamma. You have a 10 to minus 5, because this operator you see here, if I replace the mu with an electron, will contribute to mu to a gamma, either mu left or mu right. And you need a 10 to minus 5 alignment in the, if you want, a 10 to minus 5 suppression between the coupling with mu and the coupling with the electron. This is very unnatural from the point of view of any flavor structure, because you wouldn't expect such a strong alignment. So how to deal here? Well, one possibility is that the possible alternative story to the one I told you so far is that maybe there is nothing in the charged current, and there is only something special in the muons. Okay, and then this you can justify it with U1 models. Okay, models where really there is nothing. We don't explain the structure of the Yukawa coupling. We will postpone this problem to a higher scale. So the connection to the original Yukawa is lost, and you really put this U1 muon symmetry or mu minus tau as building blocks, and then like model with Z prime are back into the game. There are a lot of authors working on this, which I think it's interesting, but you lose the connection with the flavor, and I think it's really difficult to. You also have to assume that this B2 char anomalies goes away, which could well be. And what is more surprising is that the NGD have a special role for the muons, okay, or muons and taus, and a different behavior for quark lepton. So I seem to see two stories. I mean, one that goes where you put together B2S mu and B2 char, where really seems to go in the direction of unifying quark leptons and explain flavor. Or the other option is to unify B2S mu and G-2 and to give a special role to leptons versus quarks. Okay.
Okay, so then what is the status of scalar leptoquark? You have not said, I mean, you always
You're right.
commented
Sorry,
on that.
here I've been, just for reason of, well, on one hand, because I worked a lot on the vector, I like it more the vector. Well, first of all, why I like more the vector? I like more the vector because it's much more constrained. So with the scalar leptoquark, you can do many things because you have free couplings, there's new Yukawa couplings, and so you can adjust this coupling as you wish. I think there is one class of models with scalar leptoquarks which I like, which are those where the scalar leptoquarks are kind of ghost on boson of some spontaneously broken symmetry. For instance, there are among the long list of resonance which I put here, there are models of this type, which I think are interesting. Yeah, scalar leptoquark from GATT. I think it's one of the interesting possibilities. Generic scalar model, I'm less excited because of this fact. I mean, it looks like, okay, you can do. I have to say that for the scalar leptoquark compared to the vector leptoquark, there is a phenomenological problem related to this fact that here you see you contribute automatically to the two anomalies and not to BS no. But in the case of scalar leptoquark, if you want to do both anomalies, you really need more scalar and you need some conspiracy to achieve this. Well, in this case, you don't need it.
Okay. So now, just another question. So if I just want to include G- to muon and with this leptoquark, as you said, we have to invoke additional Z prime. So
Yeah.
is it possible to fit it in under any gauge group like SO10 or so, or multiple copies of SO10?
Well, there are various options. I think here I have to refer to this this work by yeah, for instance, Joe Davighi worked a lot on this, and I know that there are interesting groups which are not maybe the standard SO10, are groups where you unify electroweak and flavor groups, and then you can have these extra U1. So you can embed this into bigger groups, which actually have interesting properties.
Okay. Okay. Thank you.
Anybody else? Okay, I see here on this slide you are talking about various ES2 mu, etc. But in general, not in this slide, in this talk. I'm sorry to say this in this slide. But do you think BS2 mu gamma processes will help in any way?
Because B2
Mu gamma.
mu to gamma. Yeah, mu to gamma. It's very interesting.
BS2 mu gamma. No.
Oh,
I'm not
BS2
talking about
mu.
this
So sorry.
class.
This is best
Mu
to
gamma.
or so B2
No,
mu gamma.
BS2 mu gamma. Yes.
Yeah, that is interesting. Although I think that the precision you need to achieve it's high. So I think it's interesting. We'll add something because I think I don't think it will be a big.
It will be different types of operators that.
Yeah, will be different type of
address,
operators. Yes,
yeah.
And so you access also, for instance, to look at also possible right-handed currents. This will be interesting because therefore we still don't know exactly the size of the right-handed current, and this with gamma you have helicity enhancement. So yeah, I think it could be interesting. Yeah,
but of course it's extremely difficult.
But it's more difficult also, and especially LCB with photons is not an idle machine. Already with electrons they have problem. So, and then you have to wait for Bell, but Bell, the statistics is lower. So it's, I think I don't see a very immediate, but in the long term, maybe also with the upgrade too.
Yeah, low energy photons is always a problem at LHC. Yeah. Any experiment, CMS, Atlas, LHC.
Yes.
Yeah. Okay, I don't see anybody raising hand. So let's thank the speaker. Thank you so much for the interesting talk.
Okay.
Yeah, and hope we will have chance to visit India sometimes.
No, I will hope to visit you. Yes, absolutely.